tells me that you have worked out the problems that I had given, so that's very reassuring. I can start with that assumed. So we have our starting point then. So this is thermally density stratified fluid, the density stratification coming from heating. So it's heating induced either from bottom, in which case it's an unstable stratification, or from the top, in which case it is a stable stratification. The Boussinesq approximation, which is that keep only the lowest fluctuation in the steady state density, and then that takes part in the buoyancy term, and the rest of it is dropped. For the rest of the problem, it's like a divergence-free, that is incompressible flow, or reasonable in the lab situation where we are imagining two large parallel plates kept at constant temperatures at the top and bottom, T1 and T2, and delta T is your T1 minus T2. The equations of motion are del T U I plus Uj del J acting on Ui is minus del I delta rho plus alpha G delta T delta I3, that's the Kronecker delta, plus nu del square Ui, and the temperature fluctuation satisfies that delta T equals lambda del square delta T plus W delta T by D, and divergence free, that's del U equal to 0. So that's it. If it is rotating business, then the top equation has additional part, epsilon I j k omega j u k. And there is the other part where it's a charged fluid in a magnetic field. I don't think we'll get to talk about it at all, so forget it. All right, so now what are we going to do? We started talking about, we can play the game which we have played the first couple of days with the homogeneous isotropic turbulence with just the velocity field, and but that would be more of the same. It's important to do that, but I'll do it towards the end fast, and so that you know most of it. You can fill in the algebra. But it's more, there is the other issue over here, which we haven't talked about in details at all, which is this Nusselt number that I started talking about, which the turbulent regime, I mean, this goes through initially for very low, the driver is the Rayleigh number, which has the buoyancy on the top, and the resistors, which are the thermal diffusivity and viscosity in the bottom, and very low Rayleigh number of the order of 100 or so. You just have conduction with the profile that T0Z is T1 minus delta T over D times Z. And this delta T over here, mind you, is temperature minus the steady state profile, just as P over here is, delta P over here is P minus P0, the steady state profile. So this is the conduction. Changes over to convection, convective roles, idealized theorists picture. The reality is more complicated. So this happens at a critical Rayleigh number of this, and then to wavy rolls, then these patterns becoming problematic, to the situation which we finally want to look at, where it is almost, there is this random velocity field going around over here in some manner or other, and the temperature more or less uniform in the middle of most of the drops in the temperature taking place at this, in this small region over here, which is called a boundary layer, where it is primarily a static, at least a laminar situation. That it's a laminar situation. In this, it's not a static situation, but a stable boundary layer. It's not a convective process is not going on over here. That's the starting assumption. So there are two boundary layers. Thickness is dB for the boundary layer, and the temperature drop delta T over delta T by 2 over here, delta T by 2 over here, and in between almost uniform temperature with deviation. It's if you look at the probability of finding a temperature different from the mean value, then it sort of falls off rapidly. This is delta T, deviation from T1 plus T2 over 2, and it has the probability of the deviation has a sharp fall off. So that's the picture of the turbulent convection, and the issue is how does the Nusselt number, which is total heat transport divided by heat conducted, which is the total transport is transport by conduction plus transport by convection divided by the conduction. So this is equal to 1 plus transport by convection divided by transport by conduction. So that's the Nusselt number, and when it's very high, as there is a lot of heat being transported by convection at these very large Reynolds number. How large a Reynolds number are we talking about? It is this reduced chap, RA over RA critical, which one talks about. And you start talking about regimes which are greater than 10 to the power 3. You can push it experimentally up to these days 10 to the power 12 or 13, something like 10 to the power, somewhere larger than 10 to the power 10. So immense range of this small r. And the Nusselt number is very big, which means most of it is convective transfer. So the Nusselt number becomes, for these large Rayleigh numbers, this convective transport. And the interesting thing is that there is a scaling law, which is this. And question is, what is beta? Experimentalists can do it measure it with a lot of precision. So that's why this is now a more interesting field where theories and experiments can be compared much more easily. Doing this real experiment, not numerical experiments, but real world experiment. And unlike the spectrum, which we talked about before and which will exist over here as well, the spectra are very difficult to determine experimentally. There it is primarily numerics. And but here, It is a real-life experiment, numerics, calculations, everything gone in, and you have some. So, all right. So what can be a beta? So that what we also saw yesterday was that this is now, I mean, how much heat is transported across this boundary layer. If the boundary layer is just conduction, then the total amount of heat leaving the surface over here, that is lambda of the order of lambda delta T over dB. So that's the amount of, I mean, forget the delta T over 2, but it is of the order of lambda delta T over dB. So the Nusselt number is, barring some numerical constants over here, is d divided by dB, and there can be, I mean, numbers of order unity sitting over here. But it is primarily determined by the ratio of this height of the cell separation divided by the thickness of the boundary layer. So that's what you have to do. All right, so first draw is that, all right, this boundary layer over here is conducting. So if the boundary layer is conducting, then the Rayleigh number, what is the Rayleigh number associated with the boundary layer? The Rayleigh number associated with the boundary layer is alpha delta T G d boundary layer cubed divided by lambda times nu. So that's the Rayleigh number associated with this boundary layer over here. And you say very naively as a first go that if the boundary layer is stable, so stable boundary layer, then RA has to be less than or equal to 1708. So it is some number which is less than this 1708 over here. Mind you, that's sort of a bit of a cheat in the sense that if you try to get that 1708 by doing the procedure that Professor Govindan was indicating over the last couple of days, then you would have to look at the destabilization, critical Rayleigh for the destabilization of the conducting state which doesn't have any velocity. So it's a zero velocity heat conducting state. The boundary layer over here is not exactly a zero velocity state. There is a certain amount of flow in the boundary layer, but it's a laminar flow, not really a turbulent boundary layer. So it is a stable laminar boundary layer, and you say, all right, I mean, it's something, a Rayleigh number that's pulling, that's being a little, a bit of a cheat over here, I said, but that's a good way to start. And you find that by this argument, you can write this as alpha delta T. All right, alpha delta T G d cubed over lambda times nu times dB over d cubed. And this chap is a number.
Sir.
Yeah.
Boundary layer, the temperature difference is delta T by 2.
Huh.
So why we are when
I went through all that now, that there is a bracket over here which is of order unity, a number. So this is that dB over d cubed. For what's going on and will go on for the entire hour, numbers of order unity are not really bothersome. So we won't even, I mean, they won't bother us and we won't bother them. So mutual staying away. So, all right. So this chap is some number. So this chap is some number less than maybe, 1708, or maybe just marginal and equal to 1708. But that means, here is your Rayleigh number. This means that d over dB is proportional to r to the power 1/3. So you have your first result, which is that the Nusselt number is proportional to Rayleigh number to the power 1/3. So this was, I think, way back in the 50s, and is a reasonably good answer. So you do the experiments on transport and get the Nusselt number, and the power law dependence is indeed very close to Rayleigh number to the power 1/3. But then people started noticing deviations, increase RA, and you are going to get deviations. And so we are going to look for those deviations. I won't tell you how strong the deviations are until we get the final result. So there are deviations, and because there are deviations, I need to look at this process much more carefully. So very good. To look at it carefully, first let me redraw with these things magnified so we can all have an idea of dB, and this is D, and dB is much less than D. Yeah?
RA is dB by...
Here is RA, that's RA. RA times dB over d cubed is some number.
Okay.
Which is this. So dB over d cubed, so dB over d is like RA to the power minus 1/3, so Nusselt is d over dB, which is RA to. Rayleigh number is just, let me put a B over here for you, if you want. Rayleigh number is just Rayleigh number which is defined with the actual delta. Let me make it clear once and for all. Sorry that this confused you. This is the Rayleigh number. So that's why it was important to get the Rayleigh number over here. This is the Rayleigh number, and right. Yeah. Why do we have 1/3? Because that is the critical, as I said, that's the, if I want to have a stable boundary layer which is essentially conducting, then the critical Rayleigh number has to be lower than 1708. It is not that it is exactly what it may be, may not be, but it is some number which is less than 1708.
I mean, 1708 seems to be very precise. It's
Very?
some precise number, right?
Yeah, it is.
So it's an experimental result with a...
No, it's a theoretical result. It's also an experimental result verified to an arbitrary degree of accuracy. And you can actually prove that this conduction state becomes unstable at a critical Rayleigh number of 1708. No question of arbitrariness over there. It's a linear stability analysis. Linear stability analysis results are theoretically accurate to an arbitrary degree of accuracy, and experiments, when they actually satisfy the conditions altogether, they always verify the linear stability. So long as linear stability is concerned, getting answers may be difficult, but the accuracy of your answer is never in doubt. Experiments always bear it out. Over here, therefore, I mean, we are saying, but now 17, you see, the point that I made was that this 1708 is for the stability analysis of a state where there is no motion whatsoever. It's a state with V equal to 0 and a conduction state profile that gets modified at 70, that gets unstable at 1708. The boundary layer over here does have a velocity movement across it. There is also such a thing as a velocity boundary layer, and if when one wants to get into the issue of both of them, the assumption is that the velocity boundary layer is actually higher, I mean, has a greater, bigger dimension than the thermal boundary layer. But that's a complication, or rather, that's a way of calculation I will not use. But this is both a thermal boundary layer and a velocity boundary layer in which the velocity exists. It's not a zero velocity thing, and therefore the question of holding this boundary layer steady, having a steady boundary layer over there, would not be exactly 1708. It could be something smaller than 1708, the stability of that, thermal stability of that particular boundary layer, but it's some number. It's a number which keeps that boundary layer stable. And this chap over here, the Rayleigh number of the boundary layer, which is the Rayleigh number times this, is some number which is maybe of that order. I mean, maybe 1,000, maybe 1,200, but it is something. I mean, certainly if 1708 destabilizes the zero velocity state, it will certainly destabilize the already state which has some velocity. So, all right, I mean, that's with this as a number, you get dB over d whole cubed as 1 over Ra. So it is Rayleigh number proportional. So it is Nusselt number proportional to Ra to the power 1/3. So I start with, so now I want to get a better, as I said, there is velocity in this boundary layer over here, there are velocities over here, and we need to respect everything and get some results out. So what? So the first thing that we said was that there is fluctuation about the mean over here. So there is a fluctuation around the mean. That fluctuation is delta t. And so in dividing it out by delta t, the capital delta t, this fluctuation is going to depend on what the Rayleigh number is. And what you see is that this picture, this relative fluctuation, delta t over delta t, becomes smaller and smaller, becomes smaller and smaller as our Rayleigh number increases. So you express that by the statement that delta t over del is proportional to Rayleigh number to the power minus delta. So delta T over capital is going to become, that's the experimental observation, that as you go deeper and deeper into the turbulent zone, there is this increased Rayleigh number, the fluctuation, relative fluctuation relative to delta T, that decreases, and you use the scaling, you introduce the scaling, that delta T over capital delta T goes as Rayleigh number to the power minus delta. The Nusselt number, this scaling is generally written as Nusselt number is proportional to Ra to the power beta. So that's the standard notation for the Nusselt number and Rayleigh number scaling. It's Ra to the power beta. So it's Ra to the power minus delta over here. Very good. Now the point is that what is the velocity going to be in the center of the cell? So there is this convective motion taking place in the center of the cell. What is the RMS velocity expected to be? So I want to know what's the RMS velocity at the center of the cell, and so what am I supposed to look at? What kind of a balance? I'm supposed to look at this result over this equation over here, and I'm supposed to look at, if I'm in the business of getting a magnitude for the velocity, then I'm in the business of trying to balance terms over here. Assuming that it's sort of a statistical steady state, I don't worry about this chap over here. It is inside, in the bottom, in the middle of the cell, the viscous terms, which have this del square over here, are once again operative near the boundary. So small scales that we have been talking about. So viscosity at small scales, and so you don't want to worry about this. The nonlinear velocity term, that has to be the big chap, because that's the it's a turbulent motion inside this over here. So I'm going to estimate that as u square over d. So my estimate of this term over here is like u square over d, and the fluctuation, this your u squared delta t divided by d, and what is it to be balanced against? It is this alpha g delta t, which is the fluctuation in the temperature fluctuations in the center of the cell, giving rise to this buoyancy term over here, and it is the buoyancy balancing this chap over here. So it's this u square over d that is going to be this over here. So if I want to get a scaling for the u, then u square behaves as delta t divided by delta t times delta t. This is Ra to the power minus delta. This is Ra itself. So u behaves as Ra to the power 1 minus delta by 2. So I've got an estimate of the mean square velocity, the same for this mean square. I mean, it's the same order for u, v, and w. So it is sort of a RMS velocity estimate. It is Rayleigh number to the power 1 minus delta over 2. Pardon? This is a balance in the center of the, it's a high Reynolds number flow, my dear. I mean, the what comparison has this term with the drive in a turbulent flow with this term over here? A Rayleigh number high is automatically, in this case, a Reynolds number high, and you don't expect that this term to be driving flows in the center of the cell, na? I mean, after all, this viscosities, news are of the order of, in CGS units, 10 to the power minus 2, minus 4. If it's water, 10 minus 2, 10 minus. So this is operative once again in a region. Where are these things? I mean, it's the velocity has to be zero on the boundary. That's viscosity playing the game for you. And then it changes rapidly in what is called a boundary layer. That is when this chap is very effective. Thereafter, the velocity is not, the viscosity is no longer a player in maintaining the velocity over here. So, all right. So heat starts out from the bottom plate over here. The amount of heat reaching top of the boundary layer per unit area, per unit time is, as we had said, this divided by delta T over T. So this amount of heat reaches this this top surface over here, and now it's convected away. So from the top surface, it is convected away. So what is the amount of heat which is being convected away? The amount of heat which is going to be convected away and transported in the vertical direction is going to be W times delta T. So this would be the amount of heat convected away, average value of W times, so there are thermal fluctuations over here which are of the order of delta T. Velocity, the vertical velocity, let's say, is of the order of W. So W times delta T, that's the amount of heat which is going to be convected away. And then, I mean, so it sort of convects from here to here and then conducts back to over there. So that's the mechanism. So convected away, that's it. So brought to the surface, convected away. What's the amount which is convected away? That's this over here. So what reached me is, so there is this W delta T average, which has to be, whatever reached you has to be convected away. So you have this kind, no equalities, only approximate order of magnitude estimates now. So W delta T is of the order of lambda delta T divided by dB. So that's, now I'm going to, I have an estimate for W. I have an estimate for W, which comes from here. That this is the RMS velocity. So W scales as Reynolds Rayleigh number to the power 1 minus delta by 2. So I'm going to look at this and try to get an estimate for the scaling of 1 over dB. So 1 over dB is what I want to scale. And so my 1 over dB is going to be like W times delta T over delta T. And W, which is 1 minus RA to the power 1 minus delta by 2. And this is RA to the power minus delta. So this goes as Ra to the power 1 minus 3 delta by 2. So I have estimated my 1 over dB, and it's like Ra to the power 1 minus 3 delta by 2. All right, so now what am I going to do with this? Well, I can't do anything right now because I don't know delta. So I have to play some, I have to get another expression for this 1 over dB so that I can get the delta, remove the delta or calculate the delta. So for that, I mean, I have come from this end. I have come to the heat transported by getting an expression for W coming from this part over here and matching this, using this transport balance, that what is conducted is convected away, and have used a W coming from the center of the cell. How about using a delta, how about using a W coming from the boundary layer? So I want to, the next thing I want to do is estimate, so this is estimating W, so this is estimate center of cell. Now I want to estimate in boundary layer. And now this should make you happy. It brings in the viscosity. So the boundary layer is very thin, and therefore it is this chap which is going to win. So it is not this chap which was the dominant turbulent velocity in the center of the cell. Now the balance is in the boundary layer, and the boundary layer winner is this chap over here, and has to balance this. So what? W, nu times W, W is what I want, divided by dB square equals alpha G, what? Huh? Which delta? Yeah, very good. Right. So now here we are then, it is nu times W over dB square equal to the amount of drop across the boundary layer, which is delta T, and so it is W over D. So that's the next estimate. In this balance over here, I'm now going to use this. So this is one balance, here is the other balance, right? So all that I need to do is write things which vary and not worry about things which don't. Delta T times dB square, that's my W, times, so this is delta T divided by delta T times dB, which is of the order of unity, right? I have left only the terms which involve Rayleigh numbers and fluctuations. So dB is what I'm interested in. So here is, this tells me dB cubed, or let's say 1 over dB cubed is equal to delta T, which is RA to the power 1 minus delta. So I have got a different estimate for 1 over dB. So taking the velocity from the center of the cell, so I'm using a heat transfer balance. What is conducted across the boundary layer is getting convected away. So that's this balance over here. And then I'm estimating W in two different ways. I'm estimating W by coming at it from the center of the cell, and I'm estimating W by coming at it from the boundary layer. And I have two different expressions, they have to be equal. So 1 over dB cubed over here tells me that this is 3 by 2, so 3 by 2 into 1 minus 3 delta is equal to 1 minus delta. So this is, right, I mean, it is 3 by 2, so this is 3 by 2 minus 1, so that is half. Half is equal to, this is 9 by 2 minus 1, so it is 7 by 2 delta, so delta is equal to 1 over 7. So delta is equal to 1 over 7, and therefore my Nusselt number over here, which is this 1 over dB, that's my Nusselt number. So Nusselt number Nu is proportional to Ra to the power 1 minus delta divided by 3, which is equal to Ra. Delta is 1 over 7, so it is 1 minus 1, so it is 6 over 3 by 7, so it is 2 by 7. So you do this and you get beta equal to 2 by 7. What's the difference? 1 over 3, which is 0.33, 2 over 7, which is 0.3, 0.29 something. So a difference of 4 out of 30, which is 12% difference. But that's the difference that this deviation that the experimentalists found was indeed of the order of 10%. So you are looking at, so this was, I mean, this is late 80s, and then a huge amount of work for the next couple of decades trying to fine-tune and more fine-tune. We are so this is where experiments and theories get driven by each other. This is a 10% deviation picked by the experimentalists, taken seriously by the theorists, and when you sort of have this is not the whole story. The 2 by 7 is correct, but the real scaling over here should also have things like Prandtl number and so on, which has been merrily neglected in all this we have done. But it's a small step to do the maths of the boundary layer over here, match correctly, and get the right answer. And it is 2 over 7 with a Prandtl number scaling, so it tells you in what range of Prandtl number. Prandtl number is a big player in these things. It is PR. Prandtl number is nu over lambda. So Prandtl numbers can be from very small to rather big, so varying them in the lab from small values for example, these metallic liquids like liquid sodium, when Prandtl number is down to 1 over 10 or 1 over 100, whatever, and up to about 10 or thereabouts for certain oils and things like that. So large variation possible to track Prandtl number, but we have been absolutely quiet about it. But the moment you look at this boundary layer, Prandtl number will start playing a big role in it, and you get Ra to the power 27. So, Pardon? No, the critical Rayleigh number never came into. We have passed the critical Rayleigh number long ago. Around the critical Rayleigh number, I can't tell you anything because it is far more complicated. The zone from here to there is absolutely problematic. There can't be any If you want to do it calculationally, you have to do numerics. There is no way of giving an argument of this kind. And if you want to do it fine, that has been and will be and is of interest for various reasons. But this kind of an argument is an asymptotic argument which completely ignores all the passage that one has gone through and directly addresses what's going on over here. Has nothing to do with Rayleigh number in the vicinity of 1700. It is all about Rayleigh number very far from there. Pardon? I mean, if I were to be interested, the point is it's a question of what's the significance. I don't understand the question at all. If this is if the onset of convection is what I'm looking at, it would be critical Rayleigh number. If I'm looking at the turbulent convection, the critical Rayleigh number has been left far behind, so it's not relevant. But in the argument that you saw over here, the critical Rayleigh number was relevant because it gave answer by looking at the stability of the boundary layer. That answer is almost there, 1/3, but the experimental difference of 10% from that 1/3 is serious and to be taken seriously. It's a difference which you do see at high Rayleigh numbers, and therefore it has to be addressed. And that address now has a cartoon which is very different from the cartoon over here, that it is a situation where there is a boundary layer, there are balances in the boundary layer, there are balances in the center of the cell, and I have to go across and do a matching. And that picture is now very different. The picture of a stable boundary layer gives me the 1/3. That is not the correct answer experimentally. It is only 10% off, but then, I mean, it is when you can address 10% off, that's when you are, I mean, doing theory in a real manner. So this is a, I mean, very crude, obviously, presentation but it gets you the 2x7. And the 2x7 is one of the benchmark results in this area, which can be much more done with much more rigor. And obvious, all right, to make the further development is that if you go up to Rayleigh numbers of the order of 10 to the power 10 and beyond, this 2x7 is no longer, it starts rising. There is supposedly ultimate thing where Nusselt number is supposed to be proportional to Ra to the power half. That's sort of ultimate scaling law, valid in the limit of Rayleigh number becoming arbitrarily big. A bit controversial. One is the highest beta values obtained till now are still in the 0.3 something region, so we are very far from there. But it is certainly true that beta in the very high Rayleigh number, beta does tend to increase. So there is that feature over there. But staying within the, I'll just end this part with staying within the 2/7 law, there is this very interesting feature when it is rotating with high angular velocity. You do find a very interesting Nusselt plot. So a log-log plot of Nusselt versus Rayleigh. So a log-log plot of Nusselt versus Rayleigh for high enough Rayleigh would be a straight line with presumably a slope of 2/7. And then with these rotational, with a high rotation speed, you start seeing a break-off. Depends on how fast you are rotating, the break-offs start occurring at higher and higher Rayleigh number. And this Nusselt number now is a Rayleigh number to some power x divided by omega to some power y. Experimentally, the first experimental demonstration of this 5 or 6 years ago gave x nearly 1.2. At the same time, there were some other people doing experiments, numerical experiments, which did not give x as large as that, but still x which is significantly bigger. Over here, it is the 2/7 law. But you increase the rotation speed and you break off from that 2/7 law and fall off faster, and you have this, or numbers, various groups with various numbers, which are lower than this, but certainly much greater than 0.5, the so-called ultimate answer. So, and this remains wholly, so this is as a pretty open question still, that how to, it is within a range where this kind of argument is valid, and yet it is something which is still quite open. So this is a reasonably open problem in a reasonably accessible area. No. Yeah, right. So, all right, so that's Nusselt number for you. And now, finally, the question of the last business in this set of lectures. I want to talk about the scale invariance. So I want to look at the scale invariance of those equations that we have written down over there. That is xi equal to xi is xi prime times L, t is t prime times L to the power z, and there is a new one which is delta t, and delta t is equal to delta t prime, let's say L to the power y. Yeah, all right. So I'd want to do the rescaling, and so it is v is equal to, or u is equal to u prime L to the power minus 1yz. So I write the first one, which we have looked at before, L minus 1 over 2z, plus this one, which has to do the same way because it's really the same thing. The pressure, which has to, and now I need to do this one carefully, plus alpha g delta t prime L to the power y, and this, which we have already, the one which we have already done, is nu into L to the power 1 minus z minus, so 1 minus z and minus 2 from that, and it is del prime square vi ui prime. So that this is del t u prime plus this equal to this plus alpha g delta t prime, and then it is L to the power 1, it is 2z plus y minus 1 plus nu, and then it is L to the power z minus 2 that we have obtained yesterday. So it is nu prime ui. So it is, there is this business. So there is alpha prime then, which is alpha times L to the power 2z plus y minus 1. There is nu prime, which is equal to what we had seen that we are familiar with. And if I play the same game over here, I'll just, you can check for yourself, it is lambda prime equal to L to the power z minus 2. Now the point is that, what about the fluxes? So fluxes are the flux that we are, kinetic energy flux, which we are familiar with. So it is this chap, the del T of that. So it is epsilon, that's the flux, and it has the, so kinetic, and the other is, the other flux is of, call it maybe some kind of a potential energy, which is half delta T squared, the thermal flux, known by various words: potential energy, thermal flux, entropy flux, entropy fluctuations being proportional to square of the delta, square of the temperature fluctuations. So various ways in which you can characterize this. So there is this, and I may call, let's say, this flux phi. So there are these two fluxes now to worry about, epsilon and phi. And now the scale changes would be epsilon equal to epsilon prime L to the power 2 minus 3z. And for phi, it is, this is phi is equal to phi prime L to the power, this is 2y minus z. So here, and that's the that's the complete story of the scaling over here. But now you have, and the whole business was that who is scale invariant? Who is scale invariant? And when it was just the velocity and only Kolmogorov, then it was the fact that this is scale invariant led to a scale-dependent viscosity and so the mixing of the velocity because of this much faster time scale. And that is, I mean, spreading over a much larger region in a smaller time. But now you have a choice. You have epsilon and phi both scale invariant, or it is phi alone which is scale invariant, or it is epsilon alone which is scale invariant. So you have three possibilities. I mean, both scale invariant. So let's look at both scale invariant first. So z then is equal to 2 by 3. So both scale invariant, one where an epsilon and phi both are scale invariant, and z is equal to 2 by 3, exactly as in Kolmogorov. And what happens? What happens to your alpha? The alpha is all right, and phi. Sorry, one more step. Phi is scale invariant, therefore z is equal to 2y, and therefore y is equal to 1 by 3. So z is equal to 2 by 3 from this chap, z equal to 2, and therefore y is equal to 3. So z equal to 2 by 3, now what is alpha prime? Alpha prime is equal to alpha times L to the power 2z, which is 4 by 3, plus 5 by 3 minus 1, which is 2 by 3. So if you go to larger scales, at large scales, your viscosity becomes very big. The effective viscosity is big at large scales. At large scales, alpha dies down. So this thermal drive, I mean, why in this so-called Kolmogorov kind of fixed point, so epsilon and phi both fixed, this is your K41 behavior. Your alpha at long distances dies down, and 2 minutes or 3. So alpha dies down, and this drive, the thermal drive, is not so effective. You have the second alternative. The third one is weird. We won't talk about it. That phi alone is relevant. Phi alone is fixed. So phi is z equal to 2y. And if z is equal to 2y, that's for that. And now you want to impose that alpha has to be, alpha cannot decrease at large scale. So you want to impose the condition that alpha prime is equal to alpha, which means that y plus 2z is equal to 1, and therefore z is equal to 2y, and therefore this is y equal to 1 by 5. Y equal to 1 by 3 gives you, and with z equal to 2 by 3, the scaling dimension of the velocity field is the same 1/3 as we got in the Kolmogorov scale, and therefore over here the energy spectrum goes like k to the power minus 5 by 3. But now it is y equal to 1 by 5, z is equal to 2 by 5, and the velocity scales v prime is v is equal to v prime L to the power minus 1 by z, which is 3 by 5. So you have changed this is a different kind of scaling, and if you look at the energy spectrum, you can work it out for yourself. It is k to the power minus 11 by 5. And this is Belgiano, and more independently at the same time, Obukov. So here is a different kind of scaling which this problem can throw up. For heating from below, starting from the early 90s to till now, nobody has really ever seen this 11 by 5. The heating from below is the more pertinent, is more popular, let's say, and you never see 11 over 5. So the first time one saw 11 over 5 in this, when one reversed this and heated it from above. So this was a contribution which is important. This was the IIT Kanpur group of Mahendra Verma. So, they did in 2014 show that if you have heating from above and a stable stratification, you can see the 11 by 5 provided the provided the buoyancy term dominates this term over here. So the buoyancy term and this term, the relative relation is provided by the Richardson number. So the Richardson number has to be such that this has to dominate. So if there is a domination of that and heating from above, you do see the 11 by 5. There are subsequently another study with a rotating system which does show the 11 by 5. And why is it so is that you can look at the energy balance over here. The first thing that we did on day 1 of the lecture, look at what scales to what scales, and you can see that an unambiguous Kolmogorov flow can be achieved only if you have a flow coming from, that is, if you are heating at the top, And then you can unambiguously say that injection at large scales would mean dissipation at small scales, and you have a flow of you have a flux flowing through. So there is a Kolmogorov argument to be thought out for this, and so on and so forth. And that's about, but these are, I mean, essentially things which are in a state of change, and some things understood, some not so understood, and both for Nusselt as you push the Rayleigh number, for the spectrum as you go along. There are, I mean, there are lots of things which are which should be unfolding as the years go by. So thanks very much.